The hypothetical significance of attractive monopoles has never been seen at the Large Hadron Collider. Specialists have been searching for proof of these subtle particles. Whenever viewed, attractive monopoles would alter our comprehension of magnetic fields and could prompt critical advancements in technology, including the development of new forms of energy storage and transmission. Moreover, the discovery of attractive monopoles would provide test evidence for grand unified theories and string theories, which attempt to make sense of all fundamental forces of nature within a single framework. While the quest for attractive monopoles may seem exclusive, it embodies the spirit of exploration and curiosity that drives scientific inquiry at CERN. The search for such elusive and potentially groundbreaking particles reflects the organization's commitment to probing the unknown and expanding the frontiers of human knowledge. Another rare investigation at the Large Hadron Collider involves examining the potential presence of particles that could travel faster than the speed of light. According to Einstein's theory of relativity, the speed of light is the ultimate speed limit in the universe. However, some theoretical models suggest that particles called tachyons could exist, which would constantly move faster than light. Detecting tachyons would fundamentally challenge our understanding of space-time and causality. While most physicists are skeptical about the existence of tachyons, the search for such particles at the Large Hadron Collider is a testament to the facility's openness to exploring even the most speculative aspects of theoretical physics. The Large Hadron Collider also enables scientists to conduct experiments that replicate the conditions of the early universe, immediately following the Big Bang. These high-energy collisions create a state of matter known as quark-gluon plasma, which existed only microseconds after the Big Bang. By studying this plasma, physicists hope to better understand how the universe evolved from its initial high-energy state into the complex and structured universe we observe today. In essence, these unconventional experiments at CERN, from searching for attractive monopoles to creating quark-gluon plasma, highlight the breadth and ambition of the scientific research conducted at the Large Hadron Collider. They illustrate how CERN is pushing the boundaries of what we know about the universe and exploring new realms of physics that were previously considered purely theoretical. The Large Hadron Collider's ultimate objective is to push the frontiers of human knowledge by unraveling the mysteries of the universe. By colliding particles at unprecedented energies, it allows scientists to explore the fundamental nature of matter and the forces governing the universe. This constant pursuit of understanding the unknown reflects humankind's innate curiosity and desire to explore. The discoveries made at the Large Hadron Collider have far-reaching implications for our understanding of the universe. By probing the smallest building blocks of matter and the fundamental forces at play, these experiments expand our comprehension of the universe's origins, evolution, and ultimate fate. They offer insights into the very fabric of reality and help address some of the most profound questions about existence. Moreover, the technological advancements and scientific breakthroughs resulting from the Large Hadron Collider's research have practical applications beyond particle physics. The development of advanced detectors, computing systems, and data analysis techniques has contributed to advancements in various fields, including medicine, materials science, and information technology. The Large Hadron Collider experiments also encourage global collaboration and inspire a new generation of scientists. Researchers worldwide work together, sharing knowledge and expertise to unlock the universe's secrets. This global cooperation is a testament to the power of science to transcend boundaries and bring people together in the pursuit of knowledge. In conclusion, the Large Hadron Collider is a cornerstone of modern physics, enabling groundbreaking discoveries and pushing the boundaries of what we know about the universe. Its experiments reveal the nature of fundamental particles, forces, and the origins of matter, providing invaluable insights into the mysteries of existence. Through its technological innovations and global collaborations, the Large Hadron Collider embodies the spirit of scientific inquiry and the boundless potential of human curiosity. As we continue to explore the universe through the Large Hadron Collider, we move closer to answering some of the most significant questions about our universe and our place within it. The European Place for Molecule Research, CERN, is divulging subtleties of a new atom smasher today, something multiple times bigger and 2 times as profound. It has found 3 new particles that could assist us with figuring out how our universe was conceived and what its future resembles. Scientists at CERN have recently disclosed discoveries that turn how we might interpret the universe on its head. Beneath the surface of their groundbreaking tests lies a universe of particles and forces so odd they could be straight out of science fiction. From potential doors to different dimensions to particles that challenge the very groundworks of reality. What baffling secrets are concealed inside these tests? We should plunge into the universe of CERN and disentangle the bits of insight that could redefine our universe. The doorway to new dimensions. A wormhole could hypothetically show up out of the blue in the sky, and the explanation would be the groundbreaking investigations conducted at CERN, home of the Large Hadron Collider, LHC. The LHC is the world's largest and most powerful atom smasher, located near Geneva, straddling the border between Switzerland and France. There are secrets about this organization that the world doesn't know about. Mysteries that could potentially change how we view physics and the universe. CERN, the European Organization for Nuclear Research, operates this gigantic scientific instrument. It extends over 27 kilometers and sits deep underground. The primary function of the Large Hadron Collider is to allow physicists to test the predictions of various theories of particle physics. This includes the high-profile examination of the Standard Model of Particle Physics, which helps us understand the key building blocks of the universe. At its core, the Large Hadron Collider works by accelerating protons to nearly the speed of light before smashing them together. These impacts produce a shower of new particles, which scientists study to gain insights into the laws of nature. It was through such experiments that the Higgs boson, frequently referred to as the God particle, was discovered in 2012. This revelation confirmed how particles acquire mass and was a crucial moment in particle physics. The experiments conducted at the Large Hadron Collider are pivotal for understanding phenomena that occur under extreme conditions, similar to those shortly after the Big Bang. The data collected can fill us in more about how the universe started and evolved, and about the fundamental constituents of matter. This makes the Large Hadron Collider a player in potentially uncovering new dimensions of reality. Dimensions that could explain mysteries surrounding dark matter and the fundamental forces of nature. Such advanced experimentation at CERN doesn't come without concerns. Some hypothesize about high-energy tests, creating black holes, or strange matter that could present risks to Earth. However, CERN assures that all safety measures are met, and the scientific community closely monitors these investigations. Studies and theoretical models confirm that any hazardous situations are highly unlikely. Through its ongoing research and discoveries, CERN helps us understand the universe better and demonstrates the extraordinary capability of human creativity and collaboration in the pursuit of knowledge. Unveiling the LHC, humanity's modern marvel. The Large Hadron Collider at CERN isn't just an amazing piece of technology. It is a marvel of modern science and engineering. Situated beneath the Swiss-French border, the enormous collider runs through a tunnel 27 kilometers in circumference and as deep as 175 meters underground. This makes it the largest particle collider in the world and one of the most important instruments in the field of particle physics. The design of the Large Hadron Collider is intended to handle experiments of unprecedented scale. The primary ring of the collider, housed in a tunnel with a diameter of 3.8 meters, contains two adjacent parallel beam pipes. Each line directs protons in opposite directions, propelled by a series of superconducting magnets. These magnets are crucial for maintaining the path of the protons, bending their course at speeds close to that of light. Surrounding the beam pipes are layers of cooling systems that maintain a temperature colder than space, necessary to keep the superconducting magnets at their required operating temperature. The scale of the Large Hadron Collider is also highlighted by its use of thousands of magnets, including 1,232 dipole magnets to bend the beams and 392 quadrupole magnets to focus them. The largest and most powerful superconducting magnets used are 15 meters long and weigh 35 tons each, showcasing the massive physical scale and technological ambition behind the Large Hadron Collider. The primary role of the Large Hadron Collider is to explore the fundamentals of the universe by observing the smallest components of matter. By accelerating particles to nearly the speed of light and then colliding them, the Large Hadron Collider allows physicists to study the resulting particles that are produced during these collisions. This process helps in testing and expanding our understanding of the standard model of particle physics, which is the current best representation of the subatomic world. One of the key objectives behind the Large Hadron Collider's experiments is to uncover the mysteries of the Higgs boson. Its discovery at CERN in 2012 confirmed theories about how particles gain mass. The Large Hadron Collider additionally investigates other fundamental particles and forces, aiming to address essential questions like the existence of dark matter and the nature of the universe shortly after the Big Bang. Moreover, the Large Hadron Collider seeks to verify the existence of new particles that theoretical physics predicts but has not yet observed. These experiments continue to push the boundaries of our understanding of the universe, are fundamental for conceivably finding new physical science beyond the standard model, including supersymmetry and dimensions beyond the recognizable three spatial dimensions. The vision behind the Large Hadron Collider isn't just to grasp the universe's structure, but to cultivate global cooperation with thousands of researchers from more than 100 nations working together. The Large Hadron Collider is proof of worldwide collaboration in the mission for knowledge. The Large Hadron Collider's structure and scale enable it to tackle some of the most serious inquiries in physics. Its purpose extends beyond mere scientific interest, aiming to develop our understanding of the universe and inspire global cooperation in science. Through this colossal and complicated device, humanity continues to push the boundaries of what is known and venture into the quantum realm. But how does the Large Hadron Collider truly work? At the heart of CERN's research facilities, the Large Hadron Collider serves as a powerful microscope into the quantum domain, allowing scientists to observe and study the fundamental particles that make up everything in the universe. The process of particle acceleration and collision at the Large Hadron Collider is a key strategy for testing the foundations of physics. Inside the collider, two high-energy particle beams travel at nearly the speed of light before they are made to collide. These beams travel inside tubes kept at ultra-high vacuum, emulating the conditions of space. Superconducting electromagnets, chilled to temperatures colder than space, guide and focus the beams at designated collision points along the tunnel. These beams meet, smashing particles together with tremendous energy. The collisions produce a variety of subatomic particles, some of which are highly unstable and exist only for fractions of a second. To detect and analyze the byproducts of these collisions, the Large Hadron Collider is equipped with massive detectors, ATLAS, CMS, ALICE, and LHCb, each designed for specific types of research. These detectors capture data about the particles, including their mass, charge, and energy. This data helps physicists test predictions of particle physics theories, including the standard model, and explore particles and forces that govern the universe. One of the most significant discoveries at the Large Hadron Collider was the discovery of the Higgs boson in 2012. This particle, sometimes referred to as the God particle, is crucial because it provides evidence for the Higgs field, which is responsible for giving mass to elementary particles. The presence of the Higgs boson was predicted by the standard model, and its discovery was a tremendous achievement, confirming long-standing theoretical predictions. Beyond the Higgs boson, the Large Hadron Collider has also been instrumental in finding a range of other particles. For example, the collider has provided evidence for the presence of pentaquarks and confirmed the presence of tetraquarks, particles made up of 4 and 5 quarks respectively, which had not been seen before. These discoveries expand our understanding of hadronic matter, which is matter made of quarks bound together by the strong force, the force that holds the nuclei of atoms together. These findings demonstrate the predictive power of the standard model and also open new avenues of research in particle physics, offering insights into the behavior of matter under extreme conditions like those shortly after the Big Bang. Theoretical risks, science or science fiction. As the capabilities of the Large Hadron Collider expand, so do the speculations about its potential dangers. Two of the most discussed theoretical risks associated with the Large Hadron Collider are the creation of strangelets and the potential to spawn miniature black holes. These scenarios have captured public interest and scientific examination alike. Strangelets are a hypothetical form of matter that is more stable than standard matter. The speculation suggests that strangelets could convert any matter they come into contact with into strange matter. The fear associated with this theory is that if strangelets were created during particle collisions at the Large Hadron Collider, they could potentially trigger a catastrophic chain reaction, converting all matter on Earth into strange matter. However, extensive research and safety assessments conducted by CERN and the global scientific community have addressed these concerns. Studies have shown that if strangelets could indeed exist and were produced at the Large Hadron Collider, they would likely be highly unstable and decay too quickly to cause any transformation of Earth's matter. Moreover, cosmic rays, which are high-energy particles from space, regularly hit the Earth with energies much higher than those produced by the Large Hadron Collider without producing any strangelets. This natural experiment suggests that strangelets are not a credible threat. The idea that the Large Hadron Collider, LHC, could create miniature black holes comes from theories of extra dimensions in physics. According to certain theoretical models, the high-energy collisions inside the LHC could generate tiny black holes that would dissipate instantly due to a process known as Hawking radiation, named after physicist Stephen Hawking. Experts agree that if miniature black holes were ever created at the LHC, they would pose no threat. First, any such black holes would be minuscule and brief, dissipating before they could interact with surrounding matter. Second, the energies involved in LHC collisions, although immense by human standards, are still significantly lower than the cosmic ray collisions that occur naturally. Since no hazardous miniature black holes have been observed from cosmic ray interactions, it is highly unlikely that the LHC would produce any dangerous effects. CERN, along with independent committees, conducts thorough safety reviews to ensure that the experiments conducted at the LHC pose no risk to humanity or the planet. These reviews incorporate theoretical studies, experimental data, and safety guidelines to address any potential hazards. While the LHC's experiments continue to push the boundaries of our understanding of physics, they are conducted with a high level of responsibility and scientific oversight. This ensures that humanity can benefit from groundbreaking discoveries without facing undue risk. The theoretical dangers often sound more like science fiction than plausible scientific outcomes. The scientific consensus, based on extensive research in common cosmic events, is that the experiments at the Large Hadron Collider are safe and that the potential risks are minimal. The most fascinating experiment. One of the most intriguing and unusual experiments proposed at CERN is the search for magnetic monopoles. A magnetic monopole is a hypothetical particle that is a magnet with only one magnetic pole, either a north pole or a south pole. In contrast, ordinary magnets always have both a north and a south pole. The existence of magnetic monopoles was predicted by physicist Paul Dirac in 1931, who demonstrated that their presence would explain why electric charge is quantized, meaning it only comes in discrete amounts.